Hello and welcome back, astronomy enthusiasts. We are down to our last full week of the semester. It's been an odd one, but we have almost made it to the end. I hope you and your loved ones are all still well and healthy and staying safe. I am as well, so thank you. Some announcements. Exam 3 is in the books. The average on that exam was an 89, which is very good, and also about the same as the last exam. There is a new kappa that has been posted and will be due this Friday. It is not the last kappa of the semester. There will be another kappa that will post later this week and will be due next Wednesday, which is the last official day of classes. We have Tuesday and Thursday this week, and then Tuesday next week, and we are done with our semester in terms of classes. There will be a final in this exam, final exam in this class. It will be cumulative. It was normally slated to happen on Thursday the 17th, which was the last day of finals. We have an opportunity now to change that if we want to. I will probably post that exam maybe the Monday, that second Monday, and let you take it any day that week. It will be a format similar to the second and third midterms. We posted on Canvas, open note, open book, all of that stuff. It will be about twice as long as the previous exams. It will be cumulative, and I will be taking some questions on that exam straight off of the midterm exams. So going back and studying those is a decent idea. In terms of office hours this week, I will not be having a Tuesday office hour because that seems to be not a thing that people are interested in, but I will be here Thursday at 10 a.m. If you'd like to Zoom me, I'll post the link on the Canvas page. So without further ado, let's get back to it. If you remember where we were at the end of last week, here is a review question. Where is it? It's coming, I promise. There it is. According to the Hubble law, remember we were talking about the Hubble law, see how much you remember about the Hubble law. Which of these galaxies is moving away from us the fastest? Galaxy A, whose distance is 100 megaparsecs, Galaxy B, whose distance is 500 megaparsecs, or Galaxy C, whose distance is 1,000 megaparsecs, or if you prefer, a gigaparsec. Hope you've committed to an answer. Let's talk about the this question. The Hubble law, what is the Hubble law? The Hubble law says that the further away a galaxy is, the faster it's moving away from us. So we expect the galaxy that's furthest away, Galaxy C, to be moving away from us the fastest. And that's pretty much all you need to know for this question, the Hubble law. We're going to get back to some amazing implications of the Hubble law soon, but I want to step back a little bit and talk about another parameter that you'll often see when you're talking about the Hubble law and cosmology, and that is the redshift. We've already talked about redshift, but redshift in cosmological terms, when talking about galaxies, is defined that there's a redshift parameter. And we define that parameter to be z. And when we talk about the redshift of a galaxy, often we'll just give the z number. It'll just be a single number, and it's defined in this particular way. The redshift is the observed wavelength minus the rest wavelength divided by the rest wavelength. So the observed wavelength is where we see. So here is a star that is at rest to us, and we see these absorption features. In galaxies, those are ubiquitously shifted to the right. And so we'll take a particular spectral feature, doesn't matter which one, where we observe it in that galaxy, that's your wavelength observed. The rest wavelength is where that line would be if that object were at rest. And z is lambda obs minus lambda rest divided by lambda rest. Now, if you're paying attention, this may look familiar to you. This is, in fact, the old radial velocity formula, the Doppler shift formula. In fact, let's do this real quick. Hey, I got my whiteboard back. So I just defined z equals lambda obs minus lambda rest divided by lambda rest. That looks familiar. It should. We define the Doppler shift. This is the redshift parameter. Earlier, beginning of the semester, when we were all here and not having the social distance or anything, it was a long time ago. The Doppler shift formula, you might remember, was V over C equals lambda obs minus lambda rest divided by lambda rest. It's the same exact formula. We're just now calling what we used to call V over C, we're calling that Z. So really, Z equals V over C kind of, and V equals Z times C, if you want to multiply both sides by C. V equals Z times C. And that, if we go back to the slide, is exactly what I have written down. On the slide itself. Here it is. The recession velocity is given by z times the speed of light. Whatever your redshift parameter is, multiply that by the speed of light, and you get the true radial velocity. Okay, let's take this formula out for a spin. The hydrogen line that is normally found at 656 nanometers is seen at 1312 in a distant galaxy. What is the redshift? Oh, probably shouldn't have erased the formula that you're interested in, but I'll put it back right now. So z equals lambda obs minus lambda rest. That says rest divided by lambda rest. And we know that the line is normally found. We've got two wavelengths, and it's always confusing which is which. But in this case, the line is normally found. That means at rest. So lambda rest is 656 nanometers. That's our normal H alpha line. That's the one that was in our, that red hydrogen line. And lambda obs, where it seems in this galaxy, is at 1312 nanometers. Great, well, we can just plug this stuff in. Lambda obs, 1312 nanometers minus 656 nanometers divided by lambda rest, 656 nanometers. Let's do the subtraction first. 1312 divided by 656 is, well, look at that. I chose a number that's exactly double that. So 1312 minus 656 is, in fact, 656 nanometers divided by 656 nanometers. 656 nanometers divided by 656 nanometers is pretty easy. I can do that one in my head. That's 1. And so for this, if the wavelengths have doubled, then we expect that the z, not we expect, by definition, the z factor will be exactly 1. Doubling the wavelength means a z of 1. It's a little confusing. Tripling the wavelength would be a z of 2. Quadrupling the wavelength would be a z of 4. Great. So the largest confirmed redshift, at least in the past couple, as of about a year ago, was 11.1. We have discovered a galaxy whose redshift parameter is 11.1. So the question is, for this galaxy, we know the z, and we know where that hydrogen line is. What would lambda obs be for this particular galaxy? Well, we can solve that problem too. You'd think I'd have gotten faster at moving back and forth between these, but I haven't. There's a lot of buttons to press. Okay, so in this particular case, we know what z is. We know z is 11.1. And we know what our lambda rest is still, That's 656 nanometers. So we should be able to solve this equation for lambda obs. So let's just go ahead and do it. Z is 11.1. There's no units on 11.1. Lambda obs minus 656 nanometers. Actually, let's do something. Instead of plugging these numbers in first, let's do some algebra. Often it's easier if we solve this symbolically and then plug in at the end. Sometimes things get a little bit easier. So let's multiply both sides by lambda rest. Lambda rest goes away over here, and I've got lambda r times z equals lambda obs minus lambda rest. Now what do I have to do? Well, I need to get lambda obs by itself, so I need to add lambda rest to both sides. And I've got lambda obs, let's bring that over to the left, lambda rest plus lambda rest times z. Okay, well, I can just plug numbers in now, but I can also simplify this a little bit. I can pull out, I can make this lambda rest times one plus z. If I pull out a lambda rest and bring the 1 plus z by itself. This hasn't made my life a lot simpler, but it has made it a little bit simpler. This is an easier thing to plug into my calculator than this would have been. So I've helped myself out a little bit. This is 656 nanometers. I think it also helps to just see what's going on here, right? We sort of had that factor of 1. We knew when it got doubled, z was 1. When it got tripled, z was 2. If z is 11.1, then our lambda obs has been multiplied by a factor of 11.1 plus 1, or 12.1. This is 656 nanometers times 12.1. And that is a number that is pretty big. In excess of 6,000, in fact, 7,000 nanometers, which is about 7 micrometers. So this isn't exact, but you can plug it into your calculator and see what you get. It's on this order. This is no longer even close to the visible part of the spectrum. Remember, the visible part of the spectrum ends at about 700 nanometers. This is already near the end of it. This is way off into the infrared. Some might even call this the mid-infrared because it's so far away from the visible part of the spectrum. So that's a substantial amount. This is not a small effect. These galaxies that are very far away are moving really fast. Okay, I think that's pretty good for the first slide, the first video of the day. We'll come back in the next one and talk about the implications of the Hubble law, because they are pretty amazing and, well, they're pretty amazing. So stay tuned. We'll be back.